So, good afternoon. Welcome back after your holidays. Sorry for starting late. As you might have noticed, I was fiddling around with this small camera again. It was a sort of not complete failure last time. I got one comment saying that sound was not that good, which I agree with. The sound was not that good. That's why I'm now using it in a different configuration, which should make the sound better. And I have a microphone which I will put on after the break and see if it's still better then. So it's still an experimental stage. I don't know if any of you looked at it and found it completely unuseful or completely useful, but
it was very useful.
Okay,
very useful. Yes.
Good. So, as I said last time, if this turns out to be reasonably efficient, more efficient than I was doing just now, but then this is a good thing for us to know, because then it becomes much easier to actually record lectures. Anyway, back to the material. I hope you still remember what we did last time. That was about binary decision diagrams. And you remember then that a binary decision diagram is a directed acyclic graph, where you sort of, in order to evaluate it, you want to know if a certain interpretation gives true in this binary decision diagram by following the diagram from top to bottom. At every level you meet a proposition. If the proposition is true in your interpretation, you follow one branch. If it is false in your interpretation, you follow another. You do this until you end up at a leaf which says true or false. Then you know if your interpretation as a whole yields true or false in this binary decision diagram. And that makes it a representation of a formula, because that is just what you know of a formula, if it is true or false in a given interpretation. So, I've argued last time that it so happens that in many cases the binary decision diagram is a very compact representation of the formula, and this makes them worthwhile in practice. They are much more compact sometimes than other representations. This makes it easier to reason with them. But then, I will now finish the story by also making it clear how you can actually build such binary decision diagrams. And this long slide, and maybe imposing looking slide, tells that story, and then I'll have an example which hopefully makes it clear, even more clear. So what does this say? Suppose that I have two binary decision diagrams. Let's call them D1 and D2. So both, you can think of them as representations of formulas. Suppose that I want to build a binary decision diagram of the combined formula, for instance, where I take one and the other, or one implies the other, right? You put an operator in between. You have two binary decision diagrams. What you want is the binary decision diagram for the combined formula. Do you have the scenario in mind? The question then is, how do you build the binary decision diagram of the combined formula, the and or the implies or the or of the two original ones? And the trick here is that you can actually do this step by step by descending into the individual binary decision diagrams, and so step by step build up the combined one. How does that work? Well, if you think of it, then a binary decision diagram either is a leaf or it is not a leaf. And I have two of them, so I have four combinations. Either neither is, well, it could be that neither is a leaf, so it's a node with two descendants, or one is a node that is not a leaf and the other is a leaf, or one is a leaf and the other is not a leaf, or both are leaves. In those four cases, I have to know what to do. So it's a case distinction based on the shape of the binary decision diagrams. So what about if both my binary decision diagrams are non-leaves? So they are of the shape which I here denote P, so D1 is of the shape P, D1 prime, D1 double prime, D1 second. What does it mean? So P is my top proposition, D1 prime is the true child of the top proposition, D1 double prime is a false child. Similarly, for D2, I have a top proposition, which I assume here to be the same one, I have a true child and I have a false child. Then how do I build up the combined dynamic decision diagram? This turns out to be actually quite simple, because you still want to evaluate the proposition P. The true child is now the combination of the true children of your individual binary decision diagrams. And the false child is the combination of the false children of your two original binary decision diagrams. Yeah? I'll show it in an example later, but I hope you can already picture this in your head. That is under the assumption that I'm dealing with two binary decision diagrams, both of which have the same proposition as at the root. This does not need to be the case. I might have one that has a proposition P at the root, the other has a proposition Q at the root. Then, please remember, my propositions are ordered. So I know either P is smaller than Q in this ordering, or Q is smaller than P. Suppose that P is smaller than Q, then the combined dynamic decision diagram, I only have to look at this P part because the Q part comes later. So now what I do is I take as a root the P proposition. The true child will be the combination of the true child of my first tree together with the entire second tree. So it's D1 prime combined with D2. This diamond here is the logical operator that I'm dealing with here. It works the same for all logical binary operators, so we don't need to think about that right now. And the false child will also be the false child of my first binary decision diagram together with the entire second one. So I'm evaluating P, but my second binary decision diagram doesn't have a node for P, so I don't do anything with it. I just inherit it into the combined binary decision diagram. Third case is symmetric to the second case, entirely symmetric. And the fourth case is where both of my binary decision diagrams are both leaves. Now, if they're both leaves, then they're both either true or false. And now it matters which operator I'm actually dealing with, because I just compute the result of that operator over true and over my leaf values, and that will be the outcome of that part of the construction. Okay, I will now illustrate this. I hope it made some sense to you, but I will now illustrate it on an example. This example actually is for the exclusive OR. So here I have an exclusive OR of P exclusive OR Q exclusive OR P exclusive OR R. Okay, this is always a bit tricky to reason about, but let's just build the damn thing. And I will start by assuming that we already have the BDDs of P exclusive OR Q, and also the BDD of P exclusive OR R. But just as a refresher, let's build them on the whiteboard. So what is the BDD for P exclusive OR Q? I'll give you the first node for free. I'm now going to evaluate P. So what do I do?
P goes to Q to split.
So I get here the true branch, and then evaluate Q. I get the false branch. I also evaluate Q. Yeah? I agree. So what about this node? If I expand this further, what happens? I get a full true branch and a false branch, that's for sure. What are the children?
If it's true, then it's true. If it's false, nothing is false.
Yes, I agree. Because then, I mean, it's an exclusive OR, so either P or Q needs to be true, but if they're both true, then the whole thing is false. And that means that for this Q, P was already true, so if Q is also true, then I go to false, whereas if Q is false, then I go to true. This would be the BDD. Similarly for P, so this is the BDD of P XOR Q. The BDD for P XOR R, of course, is quite similar, except that we have R instead of Q here in the intermediate level, but that's the only difference. This is true over there. So what I want to show is how you build step by step and systematically the combined BDD of the XOR of these two BDDs. So, first case, I'm at the top, so I want to combine these two p-labeled nodes. In my combined BDD, of course, this will give rise to another p-labeled node. And where does the false branch go? Okay, now it actually makes sense to keep track of what I'm doing. It makes sense to actually label the nodes of the original BDDs. So let's label them. I'll just label this one by 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this node is actually a combination of nodes 0 and 5. If I go the true branch, where do I get? And if I go the false branch, where do I get? So let's take the true branch. What is the node corresponding to this child? Well, yes, but remember, we're actually evaluating both of these p's at the same time. So if you evaluate this p, then you get to the q node that is numbered 2. If you evaluate this p, then you get to the r node that's numbered 7. So the node that you go here to is essentially, what is it? It's a combination. So I'll number it 2, 7. It's a combination of 2 and 7. Yeah, what am I going to evaluate there?